Welcome! You're looking at a live simulation of a spacecraft's high-speed return to Earth, where we track the intense deceleration forces, G-loads, felt by the crew. You can use the sliders to swap vehicles or adjust the entry angle, gamma, to see how the trajectory and G-history change in real time. The two peaks you see are the signature of a skip entry, a technique used by the Orion. Yes, what you're seeing right now is a skip entry profile because the Orion capsule, Vehicle 3, is selected. If you switch the vehicle slider to Gemini 1 or Dragon 0, you'll see a single continuous peak. That's a direct entry typical of returns from low Earth orbit. Orion uses this exactly. During the skip phase, the capsule's lift vector is pointed upward, which literally pulls the craft back to a higher altitude, sometimes even exiting the atmosphere briefly before the final descent. This upward maneuver is what creates the lull between the two G-peaks you see on the graph. I can take you to Scene 4, Step 3, which focuses specifically on the Artemis skip entry and shows the altitude change more clearly. Shall we go there? Gemini has a wider corridor primarily because it returns from low Earth orbit, LEO, at about 7.5 kilometers per second, whereas Orion and Apollo return from the Moon at 11 kilometers per second. Lower entry speed means there's less kinetic energy to bleed off, making the undershoot limit, peak Gs, and overshoot limit, skipping out, much further apart. Additionally, Gemini, like Apollo and Orion, uses offset center of mass lift to steer. This ability to push itself down or pull itself up effectively expands the range of angles it can survive. Would you like to go to Scene 4 to see how the Gemini LEO return compares to the high? At 2.5 degrees, you are likely too shallow for Gemini. If you look at the Earth's limb on the left, the yellow entry vector is probably above the green entry corridor wedge, meaning the capsule won't stay in the atmosphere and will skip back into space. For a survivable Gemini entry, you typically want a steeper angle, around 5 degrees to 7 degrees, to ensure the atmosphere can grab the capsule and slow it down before it passes Earth. Try moving the gamma slider to see the entry vector move into the green safe zone. That nominal entry label means your current settings, even at a shallow 2.5 degrees, allow the capsule to stay in the atmosphere and reach the parachute window without exceeding the 8.5 G limit you've set. At this shallow angle, the deceleration is spread out over a long time, a wide peak, which is much easier on the crew than a steep, sharp spike. However, if you were to shallow out just a bit more, you'd see the status change to skip out as the capsule fails to capture. Would you like to see how this high-speed air also creates intense aerodynamic heating in the next scene?